Hello everyone. This is second part to my. So over here I'll be talking about one bit adder using complementary pass transistor logic. Talking about a full adder. One bit full adder is a combinational circuit that performs at two single binary numbers A and B. It takes those and it adds them up along with an input carry. So over here we have two equations, which is the sum equation and the carry out equation. So to make a full adder, we will be taking help of these two equations, and we will be constructing a circuit using complementary fast transistor logic. So moving on, complementary fast transistor logic. It is a uh, better method of making a schematic as compared to static CMOS logic, because over here we require less number of transistors, uh, and it is more efficient as compared to a static CMOS logic. Also, this helps us solve a few voltage and current drop issues. Uh, so that's why we uh, try to use a CPL logic. So looking at the sum circuit, uh, uh, so as I talked about earlier, we have this sum equation where I have A XOR B XOR C, Cn, or carry in. So that's a circuit that we have made over here. We have taken n MOSes and then we have connected them to A and A bar while giving B bar and B bar B as our inputs. And from that, we get a complemented input, more like a complemented output and a true output. When we put zeros and ones and then we draw the truth tables, so that's kind of an output we can expect from there. So when we do that, we get an output over here from our uh, first rows of some circuit, and then we would take that output and then we would again run it with our carry in, as discussed earlier. More like as we can have a look in this equation. This first circuit number one gives us the solution to A XOR B, and the second uh, circuit give us the XOR of A XOR B with Cn. So when we do that, we get our sum and some bar as our output. Moving on, we have our carry circuit. So carry circuit just moves on, takes our and, takes on more like handles our carry out operation. So over here, if you can have a look, we have this again. We have this equation, which is a E dot B, and we add it up with Cn, which goes in A XOR B, and then we get our C out equation. So we can see over here, it's a similar circuit. So we have our inputs as A bar and Cn bar, and we have A and Cn, and then we give it inputs B and B bar. So when we do that, we get a complemented solution right over here on our first circuit, and then we get a true input for our second circuit. And then we have another pair right over here where we have a true circuit, and then we have a complemented circuit for B and C bar. So when we do that, we get a bunch of equations, which when we plug in into the uh, second or I would say fifth and sixth circuits, we get our C out and C out bar. So this is how I have made the entire circuit using complementary fast transistor logic. So, as you can see, it is designed using NMOS transistors to efficiently compute and carry signals. So, this is what we have made using that principle. Now, let's have a look at the output to really see what is happening. So, this is our entire circuit. Sorry, I'll just erase this. Erase. So, we erase this, and so we can have a good look at our circuit. So as we can see, we have our inverters. We have our inverters over here. So these take A, B, and C N as our input, and they give us A bar, B bar, and C bar as an output. These are our input voltages. So VD for our inverters, and then we have A, B, C, our three inputs. This is our sum circuit, and this is our carry circuit, uh, which we had a look at a while back. So moving on our output. So as we can see, we can really test out the theory when we get uh, input 1 for A, we get input 0 for B, and a 0 for Cn. We get 1 for our sum, and we get 0 for our carry out. So which checks out, because if we had uh, one input, we had two ones, and then we were to add them up, we would always get one as our carry, and our sum as zero, because it is just binary addition, right? When we have one, when you do XOR, you get zero, and then you carry forward one. So that's the exact same logic we are having over here. So when you get one, and then you get a zero over here as our third input, when you add them up, you'll always get a carry, which is one, which is also one, and you get your sum as zero. So this checks out. So the working of this circuit is right. So yeah, that's it. Uh, Thank you for watching.